Yeah, yeah, yeah. Yeah, yeah. Got the Yeti, yeah, yeah. Yeti, are you ready? Alright, we're gonna fuck on with everybody right now. I know you guys are live streaming with me.
Thanks.
Yeah.
Thanks for coming tonight to this discussion of probably the biggest mystery in modern science. All of you and in fact the people on the web, including those students at the University of Chicago who've already emailed me to try and get their questions in early. And my job is to moderate, but also to give you a whirlwind and mind-numbing overview of this subject. So I'm planning to do that. I need to take my coat off because
I already got you flustered.
So be prepared.
I didn't mean that. I'm just excited.
Okay. We are going to talk about modern physics at its forefront. But like physics students, you can't get to modern physics without going past Newton, which is why I bought the apple. Newton learned, and he became rich and famous by learning, that in fact what goes up must come down. That fact has been true in all of science, and it became especially important in modern physics in 1929, when this guy here, Edwin Hubble, changed everything. He's one of my heroes because he gave me great hope for humanity, because he began life as a lawyer and then became an astronomer, and so there's hope. But he discovered, of course, that the universe is expanding. Yes, he looked out and saw distant galaxies. He discovered that they were an average moving away from us.
I don't know.
And the farther they were away
in terms
from
of
us,
what you're
the
talking
faster
about?
they were moving. And that implied that the universe is expanding. But that raised this question, the same question.
Where does it go? Into black
holes. If the apple
holes?
comes back down, will the universe come back down? If it's expanding, then will that expansion stop and recollapse in a big crunch, the reverse of the Big Bang, or will the universe end in a whimper as the universe expands forever? And that became the central question of 20th century physics and cosmology. And to answer that question, we can't use Newton anymore. We got to use Einstein.
You can't use either, bud.
And I want to show you Einstein's equations, okay?
But
I was told there might be a lot of biologists, so I have a form of Einstein's equations that may be relevant. So just relax.
Okay.
It'll be over soon.
I'm sorry.
So here they are. Okay. You're with me on this, I hope?
I did laugh.
Okay. The left-hand side equals the right-hand side. This is important.
Not in politics.
In fact, Einstein told us that gravity is actually related to a curvature of space. And in fact, the geometry of the universe is on the left-hand side of this equation.
Gravity has a relation with?
The geometry of the universe is affected by what's on the right-hand side of the equation, which is the mass and energy of stuff in the universe. Energy is a source of gravity. It's a source of potential curvature of the universe. And so, to answer the question, if the universe goes up, will it come back down? We have to understand that equation, which also tells us, in general, that if mass is all there is, what goes up
and the universe is a thing? We've discovered that?
Whether it'll come back down, to determine the geometry of the universe, we have to determine the total amount of energy in the universe.
You got to start with what is the universe?
Do things have enough energy by their motion to continue to expand
not a new
forever?
thing.
So we look. This is one of the more recent
You didn't even
pictures
preface
of the
it
Hubble Space
with.
Telescope, the Hubble Deep Field, one of my favorites, because every dot in that image is a galaxy, not a star.
Everything that
some of these
you
galaxies are almost 10
are seeing me
billion light years
interact with
away.
on this
The
video
question is, are they
thing
moving
is a
fast enough
galaxy,
to
and I'm
keep
just
going forever? Now, to
sucking
think
them in
about
my
that,
black hole.
we can try and measure their energy directly, or we can use Einstein's equations. We can say, well, if we want to know the term on the right-hand side, we can find out how much of it there is by measuring the term on the left-hand side, which is the geometry of the universe. So we want to try and measure the geometry of the universe.
You want to try?
Now, this is a real puzzle that
For
we've been able to
purpose?
solve in the last few years. How do you measure the geometry of the universe? How do you find out if the universe is closed or open or flat, as might be the case?
Wait, what?
And the question you want to think about is, how would you answer
How do you
the
observe?
question, how would you know if the Earth is curved, if you couldn't go around it or didn't have a satellite? Okay? And the answer is, well, you'd go to a European high school student and ask them, what's the sum of the angles in a triangle? And They tell you it's 180 degrees.
No.
But that's because they learned the geometry from Euclid. But it doesn't have to be that way. On a curved surface, things can be quite different. Here is a sphere.
Curved
and you can see
surface,
that because of
and
the curvature,
you think the planet's
three
curved or
angles of
no?
the triangle can add up to actually more than 180 degrees. In a satellite structure, because of the fact that these things are
Yeah,
coming
this is
inward,
why y'all be
these
tripping.
three angles add up to less
You
than
got the
180
wrong
degrees.
math.
And it's only on a flat piece of paper in two
That you have
dimensions,
an equilateral
things will add up
triangle.
to 180 degrees. So it turns out that that is not only true for a two-dimensional universe or a two-dimensional piece of paper, but it's true for a three-dimensional
But
universe.
not for curvature.
And in fact, if we could measure a big enough triangle, we could measure the curvature of the universe. And that's what we've been able to do in the last 15
Measure a
years or
big
so.
enough
By
triangle.
looking at the biggest triangle we can find, which means we want the longest lines we can see.
Can you create
which means we
them?
want to look out as far as we can see. And how far back can we see?
What
We can
would
see back to the
naturally
time
come?
when the universe
The
was
pyramid?
about 300,000 years old.
The pyramid.
To a time when the universe, before that, the universe was opaque. It was so hot and dense, we can't look back before that time. But at that moment, it turns out the universe cooled down to about 3,000 degrees. Matter became neutral, and the
Where?
universe became transparent. So we can look back to that time and look
Right
at
now, yeah, we
radiation
just closed the
coming
node.
at us from that time.
Quantum
That radiation
mechanics.
is now in the microwave band, so we call that
Philosopher
the
Chris
cosmic
Payne.
microwave background. We look back as far as we can, and we see that surface located almost over 13 billion light years away in all directions.
Philosopher Chris
And we
Payne.
look at that surface,
Lawrence
which was
Krauss.
created when the universe was 300,000 years old, and there's something important on that surface.
Thank you, Lawrence.
Because no information could travel faster
There's
than light.
fucking oceans.
So on that surface, created when the universe was 300,000 years old, there's a length corresponding to 300,000 light years. No information could travel further than that on that surface.
The
So if you have
length of
lumps
light
matter
years from where?
that are larger than that size, they don't even know they're lumps. Because gravity also propagates at the speed of light. They don't know what to do. They're like Wile E. Coyote when he...
And why are we doing something that was
So
about
the largest
3,000
lumps
years
that
ago?
could begin to collapse are about 300,000 light years across.
Like, what are you even
because they know they're
estimating? A
lumps.
more blurry
So if we
estimation?
can take a picture of that, an image of that background, and look at lumps, we know they're about 300,000 light years across, but we ask, how big do they look? Because if the light rays come straight at us, then that 300,000 light year across lump will span a size of about 1 degree on the sky. But if they bend, they could look bigger or smaller, depending
Light
on whether the
bends.
universe is open or closed. And that is what we've been able to do.
Open
And the
or
first
closed,
experiment that was
right.
able to
So
do
this is
that
human
the
dialogue.
Boomerang experiment. It was a satellite launched near the South Pole, went around the world at the time, which is easy to do at the South Pole. And it looked at the microwave background. And the upper image is a false color image of the cosmic microwave background. And those are the lumps, the primordial lumps that are imprinted as temperature
South Pole?
hot spots and cold spots on that microwave background. And
25
we
degrees
can create
what?
universes on a computer.
Angle photo?
On a computer, we can create a closed universe where the light rays, bend inward, and it turns out 100,000 or 300,000 light year across lump will look that big, pretty big, bigger than those lumps. In an open universe, the same physical size lump will look much smaller. It would
Yeah,
look the
'cause I'm
size of those
open-minded
blue
to your
spots,
BS.
which are smaller than those spots. But just like Goldilocks, in a flat universe, it's just right.
Yeah.
And we now know
How have you not had your life
with
a
accuracy
feeling
of
like
better
that?
than 1% that the universe is flat. And that's very important. In fact, the best image we have now,
Say that again?
and we'll talk about this later in the
You
program,
said the
comes
1%
from the
is...
flat universe. It's just right. And we now know, to an accuracy of better than 1%, that the universe is flat. And that's
The
very important.
universe
In fact,
is
the best image we
within
have
1%,
now,
the
we'll talk
universe
about
is
this later in the program, comes from the
experiencing
Planck satellite, which is
under a half
a
percent of
satellite designed to look
curvature.
over
I
the
read in an
entire
article.
sky, and these are these primordial lumps, once again seen over the entire sky, that help tell us now that the universe is flat, without a doubt.
I have
They
seen
also
that
tell us
the
something
universe,
else,
because
when
I
you
argued
look at
for...
them, you
I argued against the flat theory, and I found that one of the pressing things for like the Earth being a globe and a sphere was I could say that the universe has less than 0.5% curvature, which is like, yeah, it's not flat, but it's curved a
ask
little
yourself the
bit.
question, where did they come from? These are lumps imprinted in the cosmic microwave background that may have been imprinted at the beginning of time. They're
Lumps
the
in
lumps that will
language
eventually
speaking.
collapse by gravity to form all the structure we see in the universe today. And where did they come from? Well, it turns out we have what many physicists think is a really good theory of how to create such lumps. If there was a period very early in the universe when the universe suddenly expanded by a huge amount in a very short time, and by a huge amount I mean a factor of 10 to the 90th
Right.
in a time frame of a millionth of a billionth of a billionth of a billionth of a
How do
second.
we get that extra 10%?
That period we call inflation. Then quantum mechanics will cause these kind of lumps to form, as we may talk
No
about
shit.
later in the program.
Okay.
It will also make the universe look flat, just like blowing up a balloon makes a balloon look flat if it gets very big. If you're in Kansas, the Earth looks flat.
No, it is.
And so inflation could explain a flat universe and these little lumps,
Ask Dorothy,
but there's a problem.
the
We
Wizard
try and measure
of Oz.
everything we can see in the universe, all the stars and all the galaxies. There's not enough matter and energy to account for the right-hand side of that equation to make the universe flat.
I agree, because you're
In
just
fact,
one
what
person
we see is just literally
And
the
you're
tip
just
of a
literally
cosmic iceberg.
talking on a stage about
Inflation
shit from one
happened
point
at
of view.
very
This
early
is no
times
conflict
in this
at
picture.
all
And-
until I start
and
talking.
The universe went through a rapid period
And this
of
is where he
expansion.
goes into
And
bringing
then
up
we
inflation,
see
'cause I'm
it
inflating my
imprinted in the
voice.
cosmic microwave background. Eventually, those lumps from the cosmic microwave background will form galaxies. And so when we look
Yes,
at the universe
mine-
today, as we'll
my
talk
voice
about,
forms
we're trying
galaxies.
to go back to those earliest moments to try and test these ideas of inflation.
And the craziest part is
As I
I
say,
create a galaxy
inflation is an
between the
idea,
people that watch me and
but
you
an idea
guys.
that yet has to be fully confirmed. And one of the things it predicts is a flat universe, and this flat universe has problems because
It does.
one of the wonderful predictions of inflation that we hoped might verify it was, besides creating lumps, it also creates things that Einstein himself also first predicted, called gravitational waves, undulations in space and time. It was a
Conjulations.
remarkable prediction. And a year ago, this particular telescope at the South Pole, called BICEP, claimed to actually see the imprint of gravitational waves from the beginning of time. Potentially the most astounding measurement in the last 200 years, at least in cosmology, if it had been true. Unfortunately, the claim was not verifiable. Let me put it that way.
Conjulation.
It's not clear
Good
that it's
word.
wrong, but certainly what was claimed to be a direct observation wasn't there.
Really
So we
good
still
word.
don't know for sure if
You're right.
inflation is
You took
really
that totally a different
just
course,
a
man.
great idea,
You're
or
thinking.
actually
I'm,
corresponds
I'm
to our universe.
thinking kind of
And as I
slow
say,
right
inflation
now.
predicts
Sorry.
a flat universe.
I'm philosopher
but
Chris Payne.
it's a tip of a cosmic iceberg. This little penguin here
It
on
is.
this iceberg represents, if you compare it to the size of the whole iceberg above the water,
Mr.
the
Krauss.
ratio of normal matter in the universe compared to something we've discovered, which is called dark matter. 90%
You have
of
a
the
concept
mass
of it. I
around
can describe it for
galaxies
you.
and around clusters of galaxies doesn't shine. And if you add up everything we see, it only accounts for enough to be 3% of a universe that's flat. Well, it turns out there's a lot of dark matter, but there's another problem. If you add up the total amount of dark matter,
There's
even though it's
2/3
much
matter
more than
and
what we
1/3
see,
dark matter.
there's only 30% of the amount of energy needed to make the universe flat. So we're still missing
You're not making any
all
sense.
of that energy.
Energy to make
And
the
the
universe
question is, where
flat.
can it be? Well,
It's one person
go
that
back to Einstein's
unifies everything,
equations.
kind of like how Einstein fucked this shit up.
when he wrote down these equations, was living at a time when the universe wasn't expanding, or at least he didn't know it was
He
expanding.
didn't have the internet.
And he had this problem that gravity sucks. And if we have all this stuff out there, it's got to collapse. What could he do? Well, he added a term to the left-hand side of his equations, which he called the cosmological term. And he said that would produce a small repulsive
Right.
force throughout
So
all of
it's the
space
nature
that
of
would hold
democracy.
the universe together, and in fact, keep it from falling together.
The
Hold universe
nation,
apart.
the nature of democracy is to just clash
Well,
into
with
each
the miracle
other.
of modern mathematics, we could take a term on the left-hand side and move it to the right-hand side,
And then
for the biologists again.
the
and,
biologist
and when
Chris
we do,
Payne
what
is
does it mean?
saying
Well,
that
it's now a
humans
term
would
on the right-hand
technically
side, and that corresponds
want
to
to have
energy.
some right side
What would
sense.
such a term corresponding to the cosmological term mean? If
Nah,
it
it's
were
not
a
the
new
term,
kind
it's
of
how
energy?
humans interact,
It
sir.
would be the energy of empty space.
Empty
If you took
space.
empty
This is
space,
empty space. I
got
know
rid
you
of
hear
all
me.
the radiation and
I
all
know
the
you hear
particles
me.
and everything, empty space, if it weighed something, that would correspond to a cosmological term. Now that sounds crazy. Empty space shouldn't have energy. Except
No, it can have
in the modern
energy.
world,
It can't
empty
have
space is
mass.
so
When you
empty.
put it on digital stuff,
this is
music
an
doesn't have
actual
mass.
mathematical recreation of what the space inside of a proton looks like.
Yes, me.
Most of you who went to
I'm
school,
still in the
at
box.
regional school, learned that protons are made of quarks. But we lied. Actually, the dominant stuff that protons are made of is the virtual particles and fields that are popping in and out of existence due to the laws of quantum mechanics and relativity.
That connect
and
the
those virtual
quarks.
particles and fields give the proton at least 90% of its mass.
Yeah,
So
90% of my
these virtual
mass
particles
is
and
right.
Fields that you can't see directly give protons mass. Maybe they could give energy to empty space. Great. The problem is when we try and
Give
calculate
energy
that,
to
we come
empty
up with the risk
space.
prediction in all of
How is
physics.
it empty? There's
Come
no
up with a
such
number
thing
which
as
is so
empty
immense that
space,
we
sir.
wouldn't even exist if it was there.
There's water
But it does
molecules
lead to the
everywhere in the
possibility that
air.
empty space
I
could have
apologize,
energy.
sir.
And if empty space has energy,
Empty space does not have
everything
energy.
changes. Because remember, if empty space has energy, it
Our
produces
concept of
cosmological terms,
empty space,
and that means there's
our
a
concept
gravitational
is
pull,
that matter has energy.
and everything has changed.
And matter is
And so
all
things
around
change
us.
since-
Everything
so
has
with
changed.
Newton-
I apologize.
Newton, you have a-
But
you
did
get
you
a
really,
close-up of
are you
this
really
apple.
doing this
Look, he's
presentation
throwing
not taking into consideration
It comes
that
back
you're
down.
throwing
It
that
goes up,
through
it comes
air,
back down. Empty
oxygen?
space is everything.
Those
You
are
throw it up, it doesn't come
elements.
back down. It goes right through the ceiling.
Those are core elements
And
of
up
the
through New
elementary
York. And
table.
out into space.
Yeah.
And
Primary.
It never comes back.
It doesn't.
It
It
keeps going
doesn't.
faster and faster and faster.
And
So
you're
if
still
empty
up on
space
stage with a
dominates
paid
the energy of the
audience.
universe, everything has changed, and the expansion of the universe has changed. And in 1998, two groups of astronomers who really didn't know what they were doing at the time, they were trying to measure how fast the universe was decelerating, made an observation that changed everything.
Yes.
This is the most complicated
I'm
slide
making an
I'll show.
observation in your point.
This is measuring the expansion rate of the universe.
Okay.
And the velocity gets faster as you go further out. That's what that's what Hubble discovered. But if the universe were decelerating, those curves would bend downward. Now you can't see what's really happening there. So if you draw a straight line through those curves and make that straight line horizontal, if the universe were doing what a sensible universe should do, then these objects that they measure here, and we'll talk about what those objects are during the panel, should have followed that lower curve. These objects are supernovae, exploding stars at the far edges of the universe.
Yes.
But what they discovered to their amazement was that those objects didn't lie below the curve. They didn't even lie on a straight line. They
Kept
lived
going
above
worse. Kept
it.
going
And
down.
that would mean that that curve is bending upward. And what would that mean? That means the expansion
There's an
of the
event
universe
horizon
is accelerating.
at
It's
black
speeding
hole
up,
philosopher Chris Payne.
just like would be the case if the universe was dominated by the energy of empty space.
Philosopher
Now,
Chris
just for fun,
Payne.
if you try and fit that curve and ask how much energy you have to add to empty space, that orange curve is fit up there with this number 0.7.
Oh, 7.0, the emergence.
Have 70% of the energy of a flat universe in empty
Kate
space.
Payne 7.0,
But
I
that's
emerged.
exactly
I put
what
all
we're
my
missing.
music on Spotify and
Exactly
platforms.
what we're
Started
missing.
writing
We now
philosophy.
understand this cockamamie universe we live in has normal matter, dark matter almost 30%, but by far the dominant energy
Just
in
numbers,
the universe
random
is the
numbers.
stuff you can't see, which is mysterious and deep and dark below the ocean, in this case, like an iceberg.
You can't
70%
quantify it with
of the
numbers.
energy of the universe
Good
resides
analogy.
in empty space, and we
Good
don't
analogy.
understand why.
Good
It
analogy.
is the biggest mystery.
You don't
in
understand
science.
why you
But we
use
do
those
know
numbers? Oh my
what happens
goodness. You
if
probably don't.
that energy
And that's the
continues to
worst
be
part.
there, the galaxies we now see will move apart faster and
We are
faster
moving
and
apart,
faster.
man.
And if we wait long enough, they'll all be moving away from us faster than the speed of light, and the universe will become cold and dark and empty.
I am
That's
cold, dark, and
future.
empty
It's
right now.
visible.
Because you're not asking me.
But the good news is it's like a Dickens story. That's the future as it might be. We don't know because we don't yet understand the nature of dark energy. Until we do, we won't know the future. We won't even understand our own origins.
So why do you
That's
keep
why
trying
we
to
want
describe
know
it?
and study this subject. And that's why we brought together 5 of my colleagues from around the world who are studying this in different
shit.
ways, and I want to introduce them now. I want to introduce the first participant who was involved in the discovery of dark energy, one of 2 groups that discovered dark energy, and he shared with the leaders of those 2 groups the Nobel Prize in Physics in 2011. He's a professor of astronomy and physics at Johns Hopkins University. He's also at
Johns
the
Hopkins.
Space Telescope Science Institute. And it's a pleasure and privilege to
Space
welcome
Telescope
to the stage Adam.
Science Institute. What's up, Adam?
Okay, thanks, Adam.
Nice to have you here.
Our next participant has been involved in the cosmic microwave background for
What a
since
really good
1993.
move, man. I like
But at
this
that
guy
time,
a
the
lot.
European Space Agency got
He's
2
standing
proposals
before the others
for
with
a
courteous.
satellite to map the CMB.
Oh, he
They eventually
sits.
were combined together to form
Wait.
the Planck satellite, and He is leader of the Planck satellite mission, and it's Jan Tauber. Thank you very
Jan Tauber. Jan Tauber.
Next, we have a professor of physics and astronomy at Yale University, and who's also a professor at the Niels Bohr Institute at the University of Copenhagen in Denmark.
Whoa.
And she is looking
Niels
at something,
Bohr
another way
University,
to look at dark energy,
Copenhagen in
gravitational
Denmark.
Engine. I'm very happy to welcome Priya
International.
Natarajan to the stage.
Priya Natarajan.
Next, we have a senior staff member in theoretical astrophysics at Fermilab, and he's also a professor of astronomy and astrophysics at the University of Chicago, and a member of the Kavli Institute, and he's founder and currently serves as director of the Dark Energy Survey. Josh Freeman. Nice to see you, Josh.
Freeman. Nice.
And finally, we have the director of theoretical physics at the Perimeter Institute, and he's a cosmologist, a theoretical cosmologist who works on fundamental ideas in cosmology, which we'll talk about. And he's also founded the African Institute for Mathematical Sciences. Neil Turok, thanks for coming. Thanks. Oh, look what I found, an apple. Okay, I want to begin with you, Adam. I talked about Hubble's great discovery and of an expanding universe, and I said that things that are moving further away from us are moving faster, and that sounds suspiciously like we're at the center of the universe. So I wondered if you could, since much of your career has been involved in measuring that expanding universe directly, I wondered if you could walk us through a little bit about what that expansion means and why measuring the speed of galaxies tells us that the universe is expanding.
Sure. If you could bring up the first animation. So
Yeah.
we can look at the universe around us like a giant grid of galaxies that are expanding around us, but really expanding around everything. Maybe a good analogy is like a giant loaf of raisin bread in the oven. The galaxies are like the raisins, and if the loaf is getting bigger, no matter where you sit in this universe, everything will be rushing away from you. Now, this is a nice idea.
No,
but
because
this is something we
things
actually
rushed
wanna go
into
out
it.
and measure, verify observationally, and learn things.
No. Air.
So, following
Heat
this animation,
rushes
you
into
can
it.
see that the key to witnessing this is really to be able to measure the speed at which
See what we
galaxies
don't
move
see.
away from us. We measure this by a phenomenon known as the red shift, which you've probably heard of. This is when the wavelength of light that we know from, let's say, the laboratory arrives to us elongated or stretched by the expansion of space. We get a redder wavelength of light. We can determine how much stretching,
How
as
much
a result
drive
of
there
how
is
fast
for
that
someone to
galaxy
want to
is
pick
moving
apart
away.
something.
The other thing we want to measure to verify the pattern
Empty
is to measure
space.
how far away the galaxies are.
How far away I am
so that
to
we can
create the empty
verify that
space.
if it's really expanding, the farther away they are, the faster.
The
they
farther
will
away I am, but with your guys'
from us.
technology in this wormhole, it's
So
really
we
minuscule
have
at
to
the
use
time.
Special objects in the universe because there's no tape measures or anything like that.
So
There's
in
no
fact,
tape
as I
measures,
mentioned
yeah.
when
I don't
showed
have
your
the
data,
fucking
back to your
power
garage,
that you guys
that,
do.
These things you look at are supernovae. Why supernovae?
Right. So
I'm a
to be able to
supernova because I'm
measure
bringing
something
justice. I get what you guys do
very
is
far
good,
away,
and
we're
it gets
interested
research.
in vast distances in the universe, billions of light years, and so you can't just use ordinary stars. And it turns out galaxies are not all the same. They're sort of like snowflakes. Each one is different.
You guys are
So they
ordinary
need
stars
more
in
measuring
science.
tools. But it turns out there's a special kind of explosion that a star undergoes when a star that starts out smaller than our sun grows in mass, we think, because it lives next to another star and mass is pulled over from one star to the other. Very famous Indian astrophysicist Chandrasekhar showed in the 1930s that if a star surpasses a particular critical mass called the Chandrasekhar limit, it would explode. So this is a great, what cosmologists call standard candle. They always blow up at the same brightness. So if we can recognize them far away, just their brightness alone tells us how far away they are.
Now, okay, so
I'm
so
bright
the
as
word-
fuck.
in the 1990s.
I'm already bright for this, though.
We're trying to use that to measure literally the deceleration of the universe. Which
Right. It's probably like
but there were
0.5
problems
milliseconds.
cosmology
You
at the
guys are
time
off.
already, and there were sort of indirect suggestions that that standard model of a universe full of matter was already sort of breaking down. And as you know,
It is.
some of us even argued for some heretical possibilities at the time, which received very little attention.
Sorry.
Anyway,
Yeah, they didn't. They didn't.
I want to take you back
Bring
to
'em up.
the human aspect of science. So when you guys were doing the observations and you were a key part of the analysis team, how long did it take before you convinced yourself that this crazy, idiotic thing was really happening?
As Dr. Krauss described,
Lawrence is fine.
okay, we were looking to see how much matter was out there. Lawrence described, tossing this apple in the air and seeing it fall back down. By measuring how much the apple is decelerating.
Lawrence, my name philosopher Chris Payne.
If the apple will fall back down at all. If Lawrence could throw it hard enough, it could escape the gravitational pull, but it would always be
I'm
slow.
not trying to
So
throw
our
everybody
question
out of
really
fucking
was, the universe
confusion.
is expanding, how much is it slowing? And the way to measure this was to look out much further, because I told you we can measure how fast the universe is expanding. Well, I lied really a little. There's always a delay built in. We see the sun the way it was 8 minutes ago. We see the universe the way it was millions or
K-Pain
billions
8.0.
years ago. We can turn this to our advantage
K-Pain
by looking
8.0.
out very far and check how the expansion's been doing, how it's been slowing down. So we looked out with the supernovae with the thought that, maybe people had missed, maybe there was more mass out there. If we got out far enough, it would be
Let
decelerating.
me interrupt you for a second, because people may wonder how on earth you see supernova. I think you have some images of
Yeah.
because how do you see this object in the middle?
It's
of the
just the way I
So,
fucking act.
An individual galaxy, and these are now very distant galaxies, about 10
I know,
million
we're really
light years away,
distant,
seen with
yeah.
the Hubble Space Telescope. And,
Really
what you see is a
distant to
before
this
and after
concept.
picture. So each
Can't
galaxy,
expose
100
everything.
million stars approximately. One of those stars explodes.
Hollywood
it'll be
star?
About as bright as the whole galaxy. Actually, about
Star is a
4
word in
billion
other
times
countries,
the
man.
luminosity of the sun, the thing you see at the end of the arrow. So we look for arrows in pictures in space. And we find, no, we add those.
In fucking.
We look for these supernovae, and we use them as these beacons to tell us how far away that part of space is and how long ago.
How long ago? That's now. It's
So,
2021,
coming
boy.
Back into the mid to late 1990s, we began making these measurements with
I'm
the
Chris Payne.
expectation that we were looking for, as Lawrence said, this missing 70% of the universe, but we thought in the form of matter. And 70%
No.
extra in matter would have caused a very strong slowing or deceleration of the expansion of the universe.
Yeah, because it's
at
like
the end
just
of the
using that
day,
number.
I was, written a computer program to give me the results of the analysis, and I was thinking I'm either going to see a small number, very little deceleration, the universe will expand forever, or a big number, a lot of matter, the universe will stop expanding at some point and contract. And instead, I saw a negative number. Now, that seemed really strange, but
Yeah, because
I
you're
quickly
talking
realized
BS still.
that there can't be such a thing as negative mass. You need something else, a different kind of thing.
Yes,
What
the
Lawrence had described in
issue with
Einstein's
this is
equation
we're
as
talking
the
only.
cosmological term
We're not even
could cause
knitting.
it- could cause the universe not to decelerate, but actually accelerate.
You're not even
Now,
writing
when
anything.
you see something like this, your first thought is, I made a bug. I have a problem in my computer program. The reason you think that is because you do that like 20 times a day. I mean, science is all about making the most number of mistakes in the least amount of time.
Facts.
And so you go through that process, but at some point you go through weeks between finding that next bug, and you start thinking, I can't. Maybe it's there. I can't find it. Then you start asking your colleagues to check it. They start checking it, and at some point, after finding maybe a couple more bugs, you're
Right.
now getting the exact same answer. And then you start running through the theoretical ideas, and we got to a point where the best idea we had was the cosmological constant.
And then I came
around
through.
this time, we heard there was another team that was
Yep.
doing the same experiment.
I came
getting
through.
the same answer. Now, the odds that two different
But-
groups collecting their own data would either have the same bug in their computer program or, had both put their thumb over the lens or, whatever it was, seemed very unlikely. So at that point, we published, and the community thought this was plausible given the two groups had seen it, and that, as you said, it actually fit quite neatly. That's not something that I appreciated. I was a young guy right out of graduate school, and I had not been struggling with these cosmological problems. I was just working on this measurement.
You
Right.
weren't the only one. No.
Wow.
Um,
That's cool.
but
Cool
were-
story.
Were you surprised? I mean, as I said, a number of us have published some ideas that there were some problems, but
He went
I
to
was kind of surprised.
graduate
Maybe you
school?
were so young at the time it wasn't surprising you. I was amazed at the speed with which the community accepted this heretical result, because it flew in the face of everything that people thought was reasonable at that time. But I think people have been primed. There have been enough problems that people almost sighed and said, well, this is crazy, but at least it solves our problem. But were you surprised by the speed with which?
I was, when you do science, you do an experiment, it's kind of like being dealt a set of cards in poker. That's the hand you have to play. And we had I thought the theoretical
Good analogy.
play, and I wasn't, particularly comfortable with that as a young scientist. I mean, the only time you would be known is if you were very famously wrong. But that's what we had. And so, we played that hand, and I think it really wasn't until a couple of years later, until the cosmic microwave background observations came out in early
Wow.
2000. I saw those results, which confirmed this in a totally different way.
Yeah.
That's the first time I said, oh my God, I think we were right.
Yeah, we'll get to that. The point is, I think if it had just been supernovae,
This is wild. You
believed
just
it, and may still not believe it in a way, because there's a lot. We'll get to supernova issues, but there's a lot of astrophysics, a lot of dirty astrophysics involved, and so it's suspicious. But there are other ways to probe it, as we'll talk about, and other indications. And in fact, the cosmic microwave background, as we'll get to in a minute, played a big role, not least in showing the universe is flat, which was
it's useful though. They have
Matter
facilities,
couldn't be all there was.
connections.
It's been almost 2 decades since that time, and the cosmological constant.
Can't ignore
fit
those.
Best then. What have we learned since then? Because many of people are hoping, as we'll talk about, many of the people in the stage are trying to find that it isn't a
Sorry,
cosmological
guys.
constant, it's something different.
Right.
But
Right.
what have we learned?
So in 1998, when we discovered this, we could just say
9 is
the
God,
universe is
8.0,
accelerating.
KPN
We
8.0.
couldn't say a lot about the nature of the stuff causing this. Einstein's term was consistent, but so was a very broad range of other possibilities.
Hawking radiation,
Now,
philosopher Chris
Einstein's
Payne.
term would have a very specific amount of acceleration for a given amount of energy. And as I said at the time, we could just very coarsely tell what was going on. So now
Martin
we've
Luther
gone through
King.
about 15 years, and in that time, the data is
Mahatma
improved
Gandhi.
so much that we could say to within about 10% precision that the dark energy we see, the accelerating phenomenon, looks like Einstein's cosmological constant. So it could have
Okay.
been the case over those 15 years that it looked very different from that,
Yeah.
and we would have been able to tell that. But instead, it hews very close. It's almost a doppelganger to the cosmological
Yeah,
constant.
it's been amazing and in some sense frustrating as well, from a theoretical perspective.
So I would say that
Doppelganger.
we have passed through one order of magnitude improvement, and Einstein's cosmological constant has stood up. We think that we have the potential over the next, I would say, 2 decades to pick up 2 more orders of magnitude of improvement. Either of those
Good
is a
claim,
chance
good
for
opinion.
Einstein's cosmological constant to fall by the wayside. That's as well as we know how to do, I think. So if Einstein's cosmological constant is still standing after these 2 new orders of magnitude improvement, then we will probably be stuck with that, unless we get a clue along the way.
Yeah,
Yeah.
we'll talk
Stuck.
about why that's frustrating, and it will be frustrating, because I made the bet then, and I still make the bet now that we will not be able to measure in the lifetime of anyone on this stage that it's not a cosmological constant.
Yeah. Talking
Time I
with the
bet my house,
scientists
then
at the
Cleveland,
festival.
and no one wanted the house in Cleveland, so
Yeah.
I took the bet. But,
Talking with
okay,
the scientists
but
at the festival.
so you mentioned that you felt you believed it when you heard about the CMB, which is a perfect segue for Jan. I presented, actually showed the picture. From
He's
the
good at
satellite.
this. I'm throwing him
But
off.
that's a highly engineered picture, and it's not. You don't start and turn things on and see that. So maybe you want to walk us through a little bit what you actually have to do. To
I am
get that
engineered.
far and what it means.
I am
Okay,
engineered.
great. So we're going to shift gears and talk about a very different kind of experiment than what
Good
Alan was
intro.
talking about.
Thank
I mean,
you.
He's looking for very specific objects that look almost like points on the sky.
Points in the
in the experiment
community.
we're going to talk about, we're looking at the whole sky. So we make pictures of the whole sky.
The skies.
And what
Oh,
you're
so
seeing on
I'm
the
in the
screen
skies?
is basically a picture of the sky as it would look if we could see it with
The purple
microwave
line is
time.
me going,
And
"Ah, I'm
as
in
you
the
can
skies."
see, it looks rather messy.
And the red is
it's
my
got a lot
drive,
of
the
stuff
blue
in
is
it.
my like.
And this stuff consists
Water
of
force.
astrophysical objects largely. I mean, for example, all of the white wispy stuff. Which is,
All the white weak
is,
forces.
dust, which is emitting
I like
light
rocking Nike
within our own
Air
Milky Way.
Forces.
Now, that's not
Space
The only thing there is
forces
this image,
in
you
space.
see also very distant objects. They look like very bright, compact points.
I am a very bright
Now,
person.
So
Thank
you see
you.
a whole variety of objects in this picture, and our job here is to disentangle them.
I've seen it
and
before.
Try to separate them from each other.
Okay.
Now, the interesting thing
How are you gonna
is that,
disentangle me from this?
Distance in our eyes also
Right.
is equivalent to time, as was being explained by Adam.
No,
So
no,
if we look at a very
no.
distant object, we're also
Relatively,
seeing
I could just zone
much
out.
earlier time in the lifetime
How,
of
how,
our universe.
how do you determine
So
my
by
focus?
separating by types of objects, we can also make
Dissociate who I
differences
am,
between
what I'm trying to
layers
do.
in time in this image. This is quite a difficult job. It takes a lot of
'Cause I'm
work to
fast.
try to separate these things out. But and it's quite amazing, but we can do the job, and in fact we have
You
done
just
the
show
job.
another diagram, probably.
And what we find is this image, which I think you have seen already.
And then, yeah,
before.
the yellow
And
comes
this
out
is,
'cause that's me
in
being
fact,
like,
the
"Eh."
earliest light that you could think of making a picture of.
And we
This is
still
the
here
light
talking about it.
that was generated in the universe when it was only about 400,000 years old.
And what
The
sky
blink
is
of the
this?
eye in the lifetime of the universe. It's really almost nothing as compared to the whole lifetime of the universe. In fact, this picture is a bit misleading because if I was to put a proper color bar on this image, you would actually see nothing. You would see a completely smooth,
Colorful,
image.
colorless.
At the time this light was generated, the universe was extremely smooth. It was basically a soup of particles, and it was not, however, entirely smooth. It had these small irregularities, these small lumps, and that's what we've enhanced in this picture. So what you see,
Yeah, you guys are in a
little
lump.
blobs of color are basically differences in what we measure as temperature. But the important
You
thing
guys
is
are
what they
measures of
correspond
lump.
to
More
is
money in your
difference
pockets is more
density
temperature.
in the matter at the time that this image was generated. So in fact, by studying those little blobs, we
Studying
can
the way you talk
use
about them,
the
yeah.
physics of the universe, the properties of the universe at that time.
At the time of me
And that's,
responding, come out.
Really important. But what's more interesting, maybe, is that by using a model, we can then extrapolate further back in time.
Back info
And
of my
one of
past
the
and
questions we've been asking
associations,
ourselves
yeah.
is how galaxies arise, how structure arises in general in the universe, and it must arise from the lumps that we see in this
The
picture.
lumps of info.
But how do these lumps arise? And our theory today says
Sometimes
that
it could
they
be
arise
random.
from quantum fluctuations, which
Fluctuations.
generated at the time of inflation. So a
Inflation
long time
at the point of
before,
speaking.
this picture was generated. So the beautiful thing here is that we measure the properties of the universe at a very early time when we think we understand the physics relatively well, and from that we can deduce the properties or some of the properties of phenomena which happened much earlier than that.
Before you go on,
Much
let me see.
earlier.
So the good news you would say is that
Why not
these
focus on now,
lumps,
bud?
look like they might have resulted from quantum fluctuations, as this theory of inflation kind of predicts, and we'll get to what we mean by kind of predicts in a bit. So that's
Good, that's cool. Good for you guys.
But
I'm glad I could help
there's
you guys.
Maybe bad news for inflation because, as I pointed out
No.
in the introduction, there was this great claim for a while that one of the sort of unambiguous predictions of inflation is that there might be these things called gravitational waves permeating the universe. And
Outside
you guys,
philosopher Chris Payne.
ultimately, you're, in the sense, Planck is the one, the experiment that in some sense led people to, including the experimentalists themselves. And let me say that I view that as one of the great triumphs of science. Not a bad thing. That,
To get this
you
guy
know,
Chris Payne annoyed at
the bicep
Planck's
people end up,
facts.
you
That
know,
is a good
First of all,
phenomenon.
they claimed something radically different than Planck thought. So you're in two separate camps. But what did you do? Did you cut each other's heads off? No. Okay? You got together and actually, because both of you wanted to know what the right answer was. It wasn't a matter of wanting to be right, but wanting to know what the right answer was. But in some sense, you were able to do observations which showed that claim was not likely to be correct. So maybe you could talk about that.
Yeah, absolutely. I mean, the BICEP team did a great job, by the way, at the measurement itself, which was extremely difficult, of a very, very faint signal. And the measurement itself was perfectly fine. It was interpretation of it, which was somewhat problematic. And they had made some assumptions about some of these emissions, which I showed in the previous picture, in fact. So there is, in fact, this dust that is emitted from our own galaxy, and some of that emission can look, from the point of view of the measurement, the same, can mimic, in fact, the kind of radiation that we would expect from these primordial gravitational waves. And what happened was that by combining measurements from the two experiments, which have different strengths and weaknesses, of course, we were able to show that, in fact, you could account for most of the signal measured by BICEP only from dust. It doesn't mean that there is no evidence of gravitational waves in that measurement. There could still be a residual
Maybe
signal
for
in
the
there.
audience, it's worth telling what the signal was that they thought they saw in the CMB, and maybe you have an image of that or not. But
Well, it was a signal that has to do with the
Yeah,
property
yeah.
of light called polarization. And in fact, I do have a picture. So
I polarize
I'm going
you.
to show that to you. Polarization is a property of light. In fact, all light is polarized at some level. It gives us additional information. So this is on top of the other image that you saw before. And it's a property that is largely imprinted on this image at the same time as the temperature is. In fact, we usually, in the jargon of cosmologists, we talk about E mode and B mode polarization, which doesn't mean much to all of you. But in fact, there is a fairly strong and reasonably easy to detect part of polarization called E modes, and that's the majority of the signal that you see in this image. And you see these swirling patterns that are imprinted on light, and they represent in some way. There are different ways to represent it, but this is a nice one, which shows some kind of directionality to light, and that is basically polarization. Now, there is a faint signal of polarization, which is the B-mode polarization, and this is the one that we expect will be produced by primordial gravitational waves, that is, those things generated at the time of inflation. That's much weaker than what you see here, okay? And what we were able to show in this joint work with the BICEP team is that so far we haven't really been able to detect any evidence that there were these gravitational waves generated.
so you were lucky in some sense, again, if you go back far enough. I think many of us were surprised that anyone was able to measure anything primordial in the cosmic microwave background. In the old days, I think we all assumed that the galaxy would get in the way. The amazing thing was it didn't when it came to those primordial lumps. But what you're really saying is when it comes in the way of polarization, the galaxy really does get in the way.
It gets very much in the way, and this is an unfortunate case where nature is not very kind to us because it makes us work very hard to separate these images in these different kinds of sources.
And just for the audience, again, the point is that polarized dust can be polarized, and therefore when light scatters off it, it gets polarized. And that's why dust can do this. Gravitational waves can do it for another pretty simple reason. If a gravitational wave came through this room, it would squish the room in this direction and stretch it in that direction alternately. But in the microwave background, what that would do, if an electron was suddenly seeing space squished in this direction, it would be hotter in this direction and colder in that direction. It would see more intense radiation from one direction than another, and it would scatter that radiation in a way which would be more intense in one direction than another. And that's why gravitational waves also produce polarization. And it's a hard job, and it may be an impossible job to disentangle. We'll see.
We hope not. It really depends on the amplitude, the intensity of the signal from those gravitational waves. We don't have a good theoretical prediction for what that should be, right? And at the moment, we have put down fairly strict upper limits on what it should be, but we know we need to go further to search for it.
If you can go further and see it, then and unambiguously detect it, then it will be in some sense. Many people would say unambiguous evidence for inflation, because we'll get to that issue of whether inflation actually happened or not in a bit. But let me just ask you one question. Is it, the actual data still, we all now say, look, the original claim was wrong, which it was. But if you actually look at the data, there's still a hint that there might be primordial gravitational waves there. So maybe we're jumping on the naysayers bandwagon too quickly. Well, you don't think so?
I think
Absence of evidence is not evidence of absence.
Yeah.
I mean, just use an analogy. I mean, if your friend said, I think I see a UFO out there, and then you determine, actually, there's a weather balloon over there, your friend could go, and maybe a UFO behind it.
Yeah. But if you actually look at the data, but on the other hand, if you actually look at the data right now, it peaks at a 95% confidence level at a non-zero primordial value, which now, as physicists, if we were doctors, that would be evidence of something happening. But we're physicists, so it's not, and 95% isn't good enough, but it's sort of tempting. No. So do
Well,
you,
there is no real evidence
we'll
at
get
the
to
moment.
you why you're a naysayer in
There
a
is,
second, Neil.
there is no evidence that we, that we have gravitational waves. There was a claim, of course, by the BICEP team, which was supported on what they would claim was incomplete information at the time on what the level of polarized dust emissions could be.
How much better
Today
you
we
think
have, as scientists, what we do is set upper limits and maybe also do these likelihood curves that give us a feeling for how much of the signal that we do measure could be contributed by a potential set of gravitational waves. And that's what you're referring to. There is still the possibility that lurking in that signal, there are gravitational waves, but we have no certainty of it.
We'll have to get much better, as Adam said, in general. We'll have to, I mean, he thinks we can do 2 orders of magnitude better. I'm skeptical in measuring the cosmological term. If we got an order of magnitude better, then a lot of people would say if you push things down by an order of magnitude, then at least the simplest models of inflation are kind of ruled out. Do you think we'll be able to get there experimentally?
Well, at the moment we have a lot of ground-based experiments which are pushing very hard in that direction, and they are claiming that they will. I'm personally rather skeptical myself because I think these are very hard measurements.
Well, haven't you shown it's going to be even harder because the galaxy gets in the way? It's going to be a lot harder than people thought 5 years ago.
Yes,
But
but
they're
I
going
mean,
to be measuring at different frequencies.
People-
That's
Yeah,
not
no,
something that
it's going to be a
BICEP
lot
had
better,
done.
but the
Absolutely.
galaxy has a lot of stuff.
experimenters are very, have a lot of ingenuity, and they can design experiments that try to get around these difficulties. Now we know that difficulty is there. It's possible to try to get rid of it, but measuring from the ground is very difficult. I think personally the ultimate experiment will have to be from space to do this kind of
We'll get to
work.
the ultimate by the end, what hopes and dreams of the future. You have discovered there's more dust than we thought, but presumably you've discovered there are places in the galaxy where there's a lot less dust. Would that suggest that experimenters could look in those areas to try and eke out a primordial signal?
What we have shown is that the whole sky has some dust emission. There are some parts where there is less dust emission, and that's where we should concentrate our hopes on. But it doesn't mean that we will actually achieve it. It depends again on the level of these gravitational waves.
Okay, well that's gravitational waves. Let's move on. And I remember, so in 1937, Einstein wrote a paper, and in the paper he said, that he'd been asked to do this by some guy. He'd been asked to write the paper, even though it was a completely unimportant result that would be completely irrelevant. And he thanked if you read the correspondence to Science magazine afterwards, he wrote the publisher and said, "Thank you for publishing this little paper which this guy recommended. It's of little use, but it makes the poor guy happy." And that's how science is done. Well, he thought it would be useless, but you're devoting your career to it. So maybe you could talk about why that useless thing is actually pretty useful for you.
Should I rethink this? Just kidding. So it turns out that what was believed to be a sort of inconsequential paper was believed to be so because the measurement was very hard. And Einstein himself believed that the measurement might not happen in his lifetime. So what the measurement really is of the deflection of light by huge lumps of matter in the universe. So what is shown here is a visualization of a cluster of galaxies, which is one of the largest repositories of dark matter in the universe. And it turns out that there's so much dark matter in a cluster that it causes a little local pothole in space-time. And what that does, it bends light from objects that lie behind this pothole on their way to us. And since we have a pretty good idea of the general distribution of the shapes of galaxies, when we see distorted shapes of galaxies, distorted because of light bending or gravitational lensing by this cluster, we can actually infer indirectly the details of the dark matter distribution in the cluster itself. Now, one of the attractive things about clusters, they're very, very effective astrophysical laboratories. And what personally fascinates me about them is that they actually allow you a shot at both mysterious ingredients in the universe, both dark matter and dark energy. And it turns out that the reason that happens, that this is possible, is that the deflection of light, the strength of deflection of light, actually depends on the geometry, as you can see. because light rays have to travel huge cosmic distances to get to us. And of course, it turns out that luckily for us, clusters of galaxies are fairly rare objects. So the entire universe isn't lined up with potholes, unlike I-95, which is my local highway. And it turns out also that what we can do now with exquisite Hubble Space Telescope data, so what you really need is very, very high resolution images where you can see these distorted shapes of galaxies. So you have a single galaxy that would sometimes be stretched out into a large arc, as you see in the animation there. So in the animation, what is shown is you have a background screen of galaxies, all of which are circular in shape to start with. But then you plonk something like a cluster, a massive lump of dark matter in front, and you see the systematic distortions in shapes. Notice this animation is just to show you the range of shapes. Nothing's actually moving that fast in the universe. These are static images that you get from the Hubble Space Telescope. But you can see the plethora of shapes that you have, the distorted shapes. Now, with these shapes, we can actually reconstruct the mass distribution of the lens of the cluster of galaxies. And what is shown in the lower panel in the blue haze is the unseen dark matter in this cluster of galaxies. You see the cluster galaxies, you see the points of light that are held together by the gravity of unseen dark matter, which we can now map. So it turns out, so what we are in effect doing is we are calibrating the strength of this lens, rather like an optometrist calibrates your eyeglasses. Now, the interesting thing is the calibration is what is shown there in the top panel. As I mentioned earlier, the strength of the distortion that you see, the amount of stretching that you see is proportional to the mass of dark matter in front, the lump of dark matter, but it also depends on the light travel distances to us and the cluster, which is acting as a lens, and the distance to the object. So one fascinating thing about this phenomenon is that the pothole can be so deep that you can have a single light ray, so the single image of a distant galaxy, that gets split and you end up seeing two copies. You actually end up seeing an odd number of images. You see two magnified copies and one demagnified copy of the same galaxy. So you see three pieces that are highly distorted. They actually correspond to the same background galaxy. Now, using these very, very distorted shapes, and this is why you need the Hubble Space Telescope, because you need to pick out all those kinds of configurations that you see, we can actually map dark matter, of course, and calibrate the lens, but we also have a handle on dark energy because of the light travel distances. So it's very similar to the supernovae, where we are measuring the geometry of the universe, so the distance traveled, the angular diameter distance ratios for these distant galaxies to the cluster and from the cluster to us. So what is exciting about this new technique? Well, clusters are very complicated objects. There's a lot going on. They're very crowded places. As you saw, there are a lot of galaxies. They're colliding with each other. They're quite messy objects. But we understand their physics much better now. And the prospect is quite exciting that we may be able to discriminate the signature of any deviation from this placeholder dark energy model. So if dark energy does not correspond to the cosmological constant, we expect to see a nice, clear signal. So we may not offer the most accurate measurement of dark energy, but if dark energy was something else, we are apt to detect it using clusters of galaxies.
Now, that's exciting in principle, but let's say one was a skeptic. Let's just pretend.
Yeah.
And at least it doesn't seem, and people in the audience may say, well, isn't it strange that you're going to be able to use, you claim to be able to use this unknown dark matter to find dark energy? Does it, maybe is that a good thing or a bad thing?
I think it's a powerful thing.
Okay. But would you say that the uncertainties in dark matter distribution might be, limit your ability to
Yes, the
discriminate?
ability to map dark matter, how accurately you can map it, is one of the key limiting factors. So one minor thing that I glossed over in the picture was that you could have stuff behind the cluster that also causes little additional potholes. right? So we would need to map dark matter to great accuracy in order to exploit these cluster lenses for measuring dark energy. But that's possible. It's happening now.
Well, why don't you just sort of wrap up by saying what you've achieved? It's been going on for a little while.
Yeah.
So where are you at?
Yeah. So where we are at the moment is with data from the Hubble Space Telescope. Earlier, we mapped a cluster that goes by the name Abell 1689, which had about 50 multiply imaged objects, so very exquisite dark matter map, and we were able to confirm the prediction of a cosmological constant type dark energy. But we have new data from the Hubble Space Telescope in an ongoing program called the Frontier Fields Project, which is the deepest look ever at 6 clusters. And so with that data, we should clearly be able to start seeing sort of a signature for any deviation. So I think watch the space. In a couple of years, I think we should have some very exciting results.
So stay tuned.
Yep.
We'll come back to that. Okay, good. Now, Josh, as I mentioned, there's more than just supernova. There's more than just clusters. There's a bunch of different ways that cosmologists can use to try and learn something about this mysterious stuff. And Josh, you were a theorist that got driven to observation because it looked like, and I agree with you, probably the only useful knowledge we'll get on it is from observation. We'll see. And you've been leading this dark energy survey, so maybe you can talk a little bit about what you're doing and why.
Sure. So I think with the discovery of the accelerating universe from the supernovae, the confirmation from the cosmic microwave background, I think we realized that we needed to do these sorts of observations on an industrial scale. Adams measurements involved a few tens of supernovae. To get those next 1 to 2 orders of magnitude of precision in trying to pin down the nature of dark energy and really determine whether it's a cosmological constant or the vacuum or something else, we really need to do much more larger scales, more ambitious surveys. And so we put together a team of physicists and astronomers, now numbering over 300 people, and we've built a new camera we call the Dark Energy Camera, which you see here. It has 570 megapixels. So it's one of the world's most powerful cameras. It can, unlike the Hubble Space Telescope, it doesn't have the same resolution of the Hubble, but it can see a very wide swath of the sky, where the Hubble is very good for zooming in on very small regions of the sky and looking very deeply. So it's very complementary to what we can do from space. And we mounted this camera now 3 years ago on this telescope in Chile. It's at the Cerro Tololo Inter-American Observatory. This is the Blanco telescope. It has a mirror that's about 4 meters across. And incidentally, this was the same telescope that was the primary telescope used by Adam and his colleagues and also the other team of astronomers in the mid to late 90s to look at these supernovae and discover that the universe is speeding up. So it has a rich history. But to carry out a new survey, we needed to build a new instrument for this telescope, and that's what the Dark Energy Camera is. And so we take what we are doing, we've starting 2 years ago and continuing for the next several years, is just taking snapshots over a very broad swath of the sky, and we'll eventually have snapshots like this one of about 300 million galaxies. So I'll just go through these one by one. I hope we have enough time. That's the first one. And in addition, we will also take repeated snapshots of the same parts of the sky to discover supernovae, and we will eventually measure the distances to about 4,000 of these distant supernovae. We'll also measure clusters of galaxies like Priya is doing, and we'll use this gravitational lensing phenomenon to again try to disentangle the nature of dark energy by using the important thing to remember is dark energy sort of has two imprints on what we can observe. One is it affects distances to distant objects. That's the supernova probe. It's also the probe that Priya is using for clusters. It also affects how structure in the universe evolves. It affects how those little lumps that we see in the microwave background, how those evolve into this rich distribution of galaxies. And so the interplay, the competition between gravity and dark energy is something we can probe by doing these very large surveys.
Well, maybe you can explain something. You're taking a bunch of pictures. You're not taking a movie.
Right.
So maybe you would explain how you might talk about, if you're talking about the growth of structure,
Right.
can you see that in a bunch of pictures?
Right, so this is an example, another example, one of the first pictures we took. So what we can do with a survey like this is we take pictures through several different filters, going from near ultraviolet light to near infrared light across the optical spectrum. And so we get not only a snapshot, but we measure the colors of these 300 million galaxies. And it turns out that the colors give you an approximate estimate of the distance to these galaxies. And so we can make maps sort of in time slicings going back through cosmic history over a period of 8 to 10 billion years back into the past. And by seeing how the distribution of galaxies changes with time, how the lensing affects nearby versus more distant objects, we can try to unpack this competition over time between dark energy and dark matter.
Now, okay, and this thing's dark energy survey and all, but let's say, as I'm still betting, that you find out that you can't tell it from a cosmological constant. It won't have been in vain in some sense, you might say. How much did this thing cost?
So the project, it costs about $40 million.
Oh, so nothing, 40 million here and there.
Build the camera.
But the good thing is, it seems to me, that it's a new window. And so you might suggest that even if it doesn't tell us about dark energy, that learning those things will tell us a lot about the universe. And maybe you might want to elaborate on that a little bit.
Sure. So this is an example of one thing we've already started to learn about the universe. This isn't telling us directly about the nature of dark energy yet, but this is a map we made of about 3 million galaxies, so it's only a few percent of the total amount of data that we'll eventually have. It's data we took soon after we put the camera on the telescope. And this is a map of actually the distribution of dark matter in the universe using this gravitational lensing technique. So those very dark orange patches are where there are lots of big concentrations of dark matter. The blue areas are where there are voids or relatively empty regions in dark matter. Unlike Priya's map, this extends over hundreds of millions of light years, so it's on much, much larger scales than the very detailed fine-scale structure that Priya was showing in individual clusters. And in fact, each of these gray circles is the position of a cluster of galaxies, which is partly responsible for, it contains the dark matter that's partly responsible for this lensing. So with this kind of measurement, we're going to learn about the large-scale distribution of mass and light in the universe. We're also discovering nearby galaxies in the Milky Way. And so one of the great things about doing these sorts of surveys is, yes, we designed it to do a very particular measurement to try to understand why the universe is speeding up. But the fact that we're going to have this data on 300 million galaxies will enable astronomers to study many, many different features of the nearby and distant universe.
Priya, you had something
Yeah,
you wanted-
Lawrence, I was just trying to remind you, like, dark matter is an unsolved problem too.
Absolutely.
Just
In fact,
piping in.
In some sense, one could say dark energy's been a boon. It's a bit, because in some sense, it's motivated a lot of new experiments which might not have been performed
That's
before. And even if they don't illuminate dark energy, they'll probably tell us a lot of other things. So in some sense,
Absolutely.
it's been a growth industry because of dark energy.
Yeah.
Good,
You're
good
welcome.
job.
Yeah.
You're welcome.
No, I think, and we might just serendipitously stumble into what dark matter is with many of these
Which,
experiments.
yeah, and it's a subject of great interest to many of us is the nature of dark matter, which after all is the dominant stuff in the universe. Now, before we leave observation and move to the murky realms of theory, and we have Mr. Murky over there, but hold on. There are a few things I want to ask. So it's been kind of, to look at how fast the universe is sort of accelerating or whatever it's doing, you kind of match the expansion rate of the universe now and the expansion rate of the universe then. And it's kind of amazing that they kind of agree at all. But it's kind of interesting that they sort of don't agree too. So I know that in order to really do this, if you really want to get to know if it's a cosmological constant, you're going to have to improve every set of measurements by at least order of magnitude, maybe 2.
Yeah.
And as I'm saying, I'm betting that won't be good enough. But to get there, you've got to pin things